All right, let's talk about something in AI that honestly looks way scarier than it actually is. It's called rejection sampling. We're going to take what looks like this super complex problem and show you just how simple and, yeah, kind of elegant the idea hiding inside really is. Let's jump in. So you see this on an exam or in a textbook, right? You've got these diagrams, tables full of probabilities, a list of data, and your first thought is probably, whoa, where do I even start? And you know what? That's a totally normal reaction. It's designed to look intimidating. But here's the secret, the key to the whole thing. Behind all of that noise is one incredibly simple idea. At its heart, rejection sampling is nothing more than a filtering process. Seriously, it's just about knowing what to keep and what to throw away. That's the whole game.
Okay, so let's get specific and figure out what we're actually being asked to do here. The main goal is to figure out the chances of A being true, but, and this is the important part, only in situations where we already know for a fact that C is false and D is false.
You'll see it written in this kind of formal way, P of A / minus C minus D. All that fancy notation is really just asking a simple question in plain English. It's saying, hey, if we only look at a world where C and D are both false, what are the odds that A is true? Let's see how we figure that out. To crack this thing wide open, you only need to get your head around two little words, the query and the evidence. If you understand what these two things are, the rest of the problem just falls into place. It's that simple.
And the difference between them is super straightforward. The query, well, that's your question. It's the thing you actually want to find the answer to. The evidence, on the other hand, is the stuff you already know. It's the clue, the given helper information that gets you to the answer. So let's apply that directly to our problem. What's our query? We want to find the probability of A. That's our question. And what's our evidence? It's the fact that C is false, or negative C, and D is false, negative D. That's our helper info.
Now that we know what we're looking for and what we have, we can talk about the main rule of the game. It's this simple idea that tells us exactly how to filter all our data. And the rule is, we only, and I mean only, care about samples that perfectly match our evidence. It all boils down to a really easy two-step process. First, you're going to scan your whole list of samples, and you're going to keep the ones, and only the ones that perfectly match your evidence. Step 2, you reject everything else. Just toss it out. It's noise. And here is the most important part of that rule. Our evidence isn't just one thing. It's two things, negative C and negative D. This means for a sample to survive, it has to hit both of those conditions. If it has a negative C but a positive D, nope, it's gone. It has to be a perfect match. All right, enough theory. Let's actually do this. Let's take that filtering rule and apply it to the 8 samples we were given and see what we're left with. This is where the magic happens.
Okay, here's our starting lineup. We've got 8 samples, each with a value for A, B, C, and D. Our job right now is to be a bouncer. We're going to go down this list and only let in the ones where C is negative and D is negative. We don't care about A or B at all. Not yet.
Let's go through them, one by one. Sample 1 gets rejected. Sample 2, let's see, it has a negative C, which is good, but wait, a positive D. It has to match both, so sorry, sample 2, you're out. Sample 3 has a positive C, so that's a definite reject. But look at sample 4, negative C, negative D. Bingo, perfect match. We accept that one. Sample 5 has a positive C, rejected. Sample 6, another perfect match, accepted. Sample 7 has a positive D, so that one's gone. And finally, sample 8, negative C and negative D. We'll accept that one too. So after all that filtering, our big list of 8 has been whittled down to just 3 survivors, samples 4, 6, and 8. Everything else has been rejected. This little group is our new world, our new data set. It's the only data that matters now. Believe it or not, we've done all the hard work. We threw out all the irrelevant stuff. Now, using only our 3 accepted samples, we can finally answer the original question and calculate that probability. So, we have to ask ourselves one last question. Remember our query? The thing we wanted to find out from the very beginning? We wanted to know the probability of A being positive. So, let's just look at our 3 finalists and count how many have a positive A. Looking at our 3 keepers, sample 4 has a negative A, so that doesn't match our query. But sample 6 has a positive A. That's a yes. And sample 8 also has a positive A, another yes. So that means 2 of our 3 samples satisfy the query. So let's do the final tally.
The total number of possible outcomes in our new filtered world is just 3. And out of those 3, the number of outcomes we were actually looking for, the favorable ones, is 2.
And that's it. That is our answer. The estimated probability of A being positive, given our evidence, is 2 out of 3. We did it. We solved the whole thing.
And what we just did, that's the core definition of probability. Think about rolling a standard die. The total possible cases? 6. The favorable cases for rolling a 4? Just 1. So the probability is 1 out of 6. We did the exact same thing. The number of samples that matched our query, which was 2, divided by the total number of samples that matched our evidence, which was 3.
So let's just zoom out for a second. That problem that looked so intimidating at the start, with all its parts and pieces, was just solved with a simple 2-step filter. Filter by the evidence, then count for the query. That's the power of this method. It cuts through the noise.
And that kind of leaves you with a bigger thought, doesn't it? This whole idea of focusing only on what's relevant, on the real evidence, and just rejecting the rest is such a powerful tool. It makes you wonder what other complicated problems, maybe even in our everyday lives, could become a lot simpler if we just got better at filtering out what doesn't actually matter.